we talk about open boundary conditions. And by open boundary conditions, we are talking about if you have a boundary here, and this is your model, and then if you have some signal hitting the wall or the boundary, then if it is an open boundary, then you are tricking the model into thinking that this is open, there's nothing here. Okay, no wall here. So this is the definition of open boundary condition. It is also known as radiation boundary condition because any radiation hitting this wall will be radiating out. Okay, so this is the meaning of radiation boundary condition or open boundary condition. Okay. Okay, so next we will apply the boundary conditions for shallow water system, and we can rewrite the linearized shallow water equations with the affection and without the Coriolis force. So eta is the wave height. If you already forgot what the variables are, you should refer to lecture 6. Okay, so this is originally this one. Okay, and this is originally this one. Eta okay, we have rewritten the mean value of your variable into the big U here, and you can see that the two equations here actually they are coupled. What does it mean by coupled? It means that each of the variables are present in both of the equations. The two variables, each of the variables are present. For example, here, and here, they are both present in the same equation, and also for this. So we will now apply a method to decouple them. So we want to separate them into two variables and two equations. How do we do that? We can rewrite the equation into the matrix form. Okay, we are rewriting these two into the matrix form. And this is the same form as the affection equation. In this form. This is Q. Q is a vector of U and eta G. Okay. plus so this matrix is this A, okay? And then we could do something to the Q and then to A to decouple the two equations here. How do we do that? We can multiply Q by this matrix. This is basic linear algebra actually, okay? So we multiply Q. What is Q? Q is this U and then eta G matrix, and then multiply this that will equal to U minus eta G over C, and then U plus eta G over C. Okay, and then this is the first thing we do to Q, to the vector Q, and then for vector A, we need to do something else first, since this vector, this matrix, multiply this one, another matrix, will be the identity matrix. We can multiply A by the identity matrix. Okay, so if you're multiplying the identity matrix to a matrix, then it will equal to itself. Okay, you are just changing the appearance of that matrix. Okay, so A equals to then you know the value of A, right? A is in here. This one is A. Okay, so if we now do the multiplication, okay, this is the result. And then it will be equal to U 272 minus and then this one minus C over 2 plus. Okay, so now we finally have the value. We didn't change the value of the vector or the matrix A. We are just changing its appearance. So we finally have the appearance of this. right? So now we can rewrite the equation, right? Okay, so we rewrite this equation by d and e. What is d? D is u minus eta g over c, and e is u plus eta g over c. Okay, we have the expression for q plus this u minus c, 0, u plus c, d and e. Okay, so this is the decoupled version in here. Why do we change it from the coupled version to the decoupled version? Because it's more solvable. It's easier to solve this equation. And each of the decoupled equations is well posed if a boundary value is provided at the inflow and no value is specified at the outflow. We have to specify the boundary condition for D and E when they are when it's having its inflow at a boundary. So for the 1D model here, so it's 1D from x equals to from 0 to L, we have two boundaries, right? So if U is larger than 0, in this lecture we only assume that U, the big U, is larger than 0, is positive. And if C is less than U, then it would be very easy to determine the inflow and the outflow, right? Because C is smaller than U, so in both of these variables, both of these affection, they are both of the affection of D and E, they are inflowing into this domain on the left boundary. So the dark red situation here for the both of the variables. Okay, and then D and E should be specified at x equals to 0 because they both of the variable are inflowing from this boundary. Okay, and then none should be specified at x equal to L because we can always calculate that. Okay, and in another situation where the big U is positive and C is larger than U, then it's a little bit more complicated because for this dark green situation, U plus C is still larger than 0. U plus C is what? U plus C is the affection of the variable E, which means that E is inflowing in this boundary, in the left boundary. Okay, and C is larger than U, so which means that U minus C is negative. Okay, so this is negative. It's totally should be totally on the other side when we are talking about the affection of D, which means that D is inflowing on the right boundary and outflowing on the left boundary. Okay, then it's a little bit more complicated when you set the boundary condition. Okay, so it depends on the value of U and C. And we should always specify the variable when it's directed inward at a boundary. Okay, so what we can do is that if C is larger than U, in many geophysical applications, C is larger than the absolute value of U. And because U is like a background flow, and when you do an average over a large set of data, the value is likely to be smaller than the weather system that you are focusing on. Okay, so if we are having this situation, we need to specify the inflow of E at x equal to 0, right? And then when we are talking about the inflow of D is from the right boundary, right? So we need to specify the boundary condition for D at x equal to L. And then they could be represented by also by the outflow, because if there's something, D is inflowing on the right hand side and outflowing on the left hand side. So this is the outflow of D, and it could be affecting what you have on the boundary for E, right? Because they are actually depending on each other. Okay, and then what we can do is that we can write a general form of boundary condition for E in terms of the outflow, and then another term which is representing the external forcings. So this is like a general situation. So if you have, it depends on what situations you're looking at. Okay, but this is a generalized function. Okay, the two function here. And if we rewrite this, the expression for E with U and eta, it will be looking like this. And then it equals to the external forcing. So alpha here represents the ratio between the boundary conditions we need. Okay, if alpha equals to -1 for this equation, which means that we don't need the boundary condition for eta. We only need the boundary condition for U. And if alpha 1 equals to 1, which means that this term is 0, we don't need the boundary condition for U, and we need the boundary conditions for eta. And if it's 0, then we need this one instead. Okay, and we can put this back to the equation, and then we can find out the boundary condition we need. So this could be representing the data from the outer domain or the lower resolution domain. Okay, so imagine that if you have a 1D model here, and this equals to x equals to 0, and then this in here x equals to L, and okay, open. And in here we have G equals to U minus eta G over C, and E equals to U plus eta G over C. And then sorry. Okay, so if you are talking about the inflow of E, this is time, and then this is x naught. And then we know that it depends on the initial condition. And then the boundary condition of E here determines the values in the right region, and then the initial conditions will affect the region in a gray area. And then the slope here is plus. Okay, and for C, larger than the value of u, as in many geophysical applications. The incoming d x equal to L. So by the way, d is incoming on the right hand side. Okay, so how does it propagate? If you have, so this is d, and then it should propagate like this. And the slope here is okay. So the incoming d at x equal to L, the big L, should be 0 for all time. Why is that? We should set d equals to 0 here, because there should be nothing coming in on the right hand side. Your equation u, we assume that it's larger than 0, right? So that's why we need to set d equals to 0. And hence in the wedge shape region in here, right, u because we have set d equals to 0 at x equal to the big L. Okay, so hence the outward E at x equal to L and near x equal to L. Okay, so we can substitute what we have just found in here, right? Substitute this into this equation. And then the radiation boundary condition for u at x equal to L. So we are making use of u xt equal to eta. Would be u partial u partial t plus u plus c partial u partial x. Okay, we can substitute either eta or u in the equation, and then we can find out the radiation boundary condition for both U and eta. Right? Okay, what does that mean? It means that at x equal to L, we can apply these at the boundary. To make the boundary open. Okay, and similarly, at x equal to 0, E should not be going out on this side. And then we can set E to 0 and with a similar method. And then we can find the boundary condition at x equal to 0 to make it an open boundary. Okay, if you specify these conditions in the boundary, you will not find the reflecting signal because it's open, right? Okay, that's how we can find the open boundary condition for this side and then for this side. All the reflection in the right boundary may be eliminated by ensuring that no leftward propagating waves are present at the boundary. So we are setting the leftward propagation waves to 0. So that's why when we are setting it, there's nothing going to the left side in here. And then similarly, if we do the same for this, in theory, your signal will be just going like this, okay? Okay, so there are other, unfortunately, if you have a model with more than one dimension, 2-dimension or 3-dimension model, 3-dimensional model, you cannot do you cannot set an open boundary with it. This like an analytical method. Okay, we have to do something else. For example, we can use an absorbing layer or what we call a sponge layer surrounding the boundary. So the points added are wasted. We are not using the data in this sponge layer. The same questions are solved. Same equations, sorry, this is a typo, are solved except with an extra dissipation term. So if you have an equation looking like this, we have some other terms, for example, advection or pressure gradient force or Coriolis force. We add another term here. It's called artificial viscosity. It's not real. We are putting it here so that the change here will dissipate in this region and nothing is coming back. Okay, so the artificial term should be turned on smoothly, so we should not turn it on 100% in here. We should turn it on like, for example, 10%, 20% like this, and then full scale at this boundary. Then we can ensure that nothing is coming back to the model domain. So we mostly implement this at the top of the atmospheric model to avoid the reflection of vertically propagating waves. Sometimes the gravity waves, they propagate upward, and we don't want that to be coming back down because there's no real boundary at the top. Okay. There are some examples. For example, if we do 2 simulations, this one is with 2.5 degree resolution for the whole domain, and then this one is with a 5 degree, a lower resolution, and then we run a higher resolution in the middle, as a nested domain. So this is a nested domain. We have a low resolution on the outside and a high resolution in the inside. And then we have the results of both of these two experiments, and then we take out the data in this region and we take out the data in this region, and we found that they're different. So this one is supposed to be better because we have the whole domain with a higher resolution, and you can see that the error is propagating first of all from the boundary. So this shape is due to the map projection. Okay, this is the error or the difference between these two simulations. You can see that something is different starting from the boundary, and then this propagate inward into the domain. Okay, so error travels into the domain. The boundary, why do we have a problem like this? The boundary is set near the regions with large variations, which means that if we have something changing really quickly, we should not put the boundary here, because the boundary conditions cannot handle the drastic changes in the variables. Okay, so here is another example showing you different simulations with different size here. So 1, 2, 4, 8, 16, there are different simulations. And in here, I'm showing you this because we should know that the boundary should be at a certain distance away from the weather systems that we want to look at. Okay, so if we have like a cyclogenesis situation, you don't need to care about what cyclogenesis is. So at the higher level, we should be seeing this large speed area region. Okay, this is from the experiment of this domain, and then we only take out the data from this box because for experiment 1 we only have data inside this box, so we can only compare the data within this region. Okay, and you can see that for this is a graph showing you the growth of error, okay, root mean square error with time. And you can see that for the 16 here, which is the largest domain, the error flats off after a while, and the error for experiment 1 increased a lot comparing to 16. Okay, which means that if you have a weather system coming in and your boundary is setting at a location where your weather system is happening, so apparently this is extending from outside, right? If you set a boundary here, then there will be a lot of error happening. And you can see that this one has a larger error value comparing to this 16. It's not as accurate as this one. Okay, I'm sorry I told you that method 3, 4, 5 is optional. Actually, it's not. You should be able to work out the virtual reflection rates for these 3 methods for this 1D model. And then for exercise 2, you need to redo lecture 5, exercise 3. We write the program with boundary conditions of method 2 and method 5 and one-way wave equation. So what is one-way wave equation? It should be this one. Okay, I've already given you the boundary condition, the open boundary condition. Okay, and prepare a table showing the root mean square error for the reflected signals for time steps 750, 800, 850 with the increment of 50 until 1200. Okay, exercise 3 is that if we are considering the one-way wave equation operator the continuous case. So this is, I'm not showing you the whole equation. So this is a function representing the waves traveling to the right. So this is a function. This is not a variable. And then this part is representing the waves traveling to the left. Okay. And then as at x equal to L, which is this side, the right-hand boundary, the one-way wave equation does not permit solutions of the form going signal going to the left, because we don't want reflection. If it's going to the left, then it's reflection. You have to prove this by showing that the right traveling part of the solution satisfies this, while the left traveling part does not. Okay, focus on this side.